Okay. Well, welcome everyone to, I think this is the last talk of TCS Plus for the semester. We're super excited to have Pravesh Kothari and Ankur Moitra here. They'll give us a talk about robust learning of arbitrary Gaussian mixtures. And just before we get started, let me just say, please feel free to unmute yourself and ask any questions throughout the talk. You can also ask questions through the chat, and David and I will be monitoring the chat. What else? Please keep your cameras on if you feel comfortable. They'll give Pravesh and Ankur some visual feedback. And finally, let me just thank the rest of the organizers of TCS Plus. This includes Clement Kanan, Rachel Cummings, and India Day, Sumega Garg, Gautam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, Noah Stevens Davidowitz, and Tomas Vidik, and David, who's also here. But with that being said, I think the formatting is going to be that Pravesh will give the first part of the talk for around 45 minutes, and then Ankur will give the second part of the talk. So yeah, please, Pravesh, take it away.
All right. You can hear me fine, right? You can hear me, right? Okay, good.
Yeah.
Thanks to the superb list of organizers for TCS for inviting Ankur and me for this double feature talk. This work on robust learning of arbitrary Gaussian mixtures, in my opinion, represents a culmination of a line of work that I and a bunch of others have been involved in this area of robust statistics. So I'm super excited to talk about it today. And what I'm going to present is joint work with some amazing co-authors. So Anish Bakshi and Hejia are the PhD students who worked very hard and got this somewhat technical work completed, and along with my other co-authors, Elias Daiko-Nicolas, Daniel Kane, and Santosh Vempala. So in terms of organization, what I'll do is I'll present to you the results, and I'll tell you a little bit about the ideas that go into it in our solution to it. And then Ankur will take over and tell you the rather different and cool ideas that they have for solving the same problem. Okay, so let me start by, the vanilla version of this problem. I'm soon going to give you a twisted version of it. Now, you probably have seen this problem of learning mixtures of K-Gaussians before, but even in that case, we will use this slide to set some notation that we will use throughout the talk. So, it's a certain statistical estimation task. The input is going to be, in this vanilla version, a sample from a d-dimensional mixture of K-Gaussians. And so, this mixtures of K-Gaussians is basically a parameterized family of probability distributions. Each of them is specified by K sets of triples of parameters, Wi, which are like weights in 0, 1, mean vectors mu I in d-dimensional space, and covariance matrices sigma i's. Given such a set of triples, the distribution they define is simply the following, which I'll describe to you by giving you a simple mechanism to sample from it. You just pick like an index from 1 through k, by picking ith index with probability wi, and then just sample the Gaussian with mean mu I and covariance sigma I. Okay, so that's the distribution. You're given samples from this distribution, and your goal is to come up with estimates of the parameters so that the resulting Gaussian mixture that you output is close to the input Gaussian mixture in some precise sense, okay? And the precise sense of closeness that we're going to use is, this information theoretic notion of total variation distance. In this setting, it turns out to be the strongest possible kind of guarantee you can hope to get. And if you've seen various special cases of these problems and talks on it, you may have seen results stated in terms of norms or error guarantees in terms of the parameters. Without going into detail, let me just say that, the kind of guarantees in total variation distance we're looking for will imply all those norm guarantees to the best extent possible, okay? Good, so one quick note about two different variants of these problems, and I know that Ankur is gonna talk about this in way more detail. So the problem that I described right now is called as the proper learning problem, because the goal is to output a Gaussian mixture of K components, which is close in total variation distance to the input. There is a related stronger variant of the problem where the guarantees, the required guarantees are somewhat stronger. It's called the parameter recovery version, where instead the goal is to output sets of parameters such that each component Gaussian is close in total variation distance to the corresponding component in the input. So, it's like a component-wise guarantee instead of just the total variation guarantee on the two mixtures. So I'll speak very little about, this distinction between these two kind of questions when I talk about the results, but, we will largely be agnostic agnostic about the distinction, in the first 45 minutes. Good. So, the usual spiel, this is an extremely well-studied problem. Probably the first statistical model, which has been studied in modern statistics, beginning with Pearson in 1894. And, there's a large sequence of works, but, if we care about provable algorithms for estimating this model, then this line of work was begun by Sanjoy Dasgupta in 1998. And, there's a quick succession of works that follow up while making, less and less restrictive assumptions on the component Gaussians and giving algorithms for them. Eventually resulting in these, breakthrough works of Ankur and Greg Valiant, and independently by Belkin and Sinha in 2010, that basically resolved this question, the vanilla version that I talked about here. And because this result is like so central to us as a starting point, let me actually tell you the result. Okay. So what they proved is that there is an algorithm for learning k GMMs, so arbitrary mixtures of k Gaussians, up to some parameter delta in total variation error. So think of delta as like some parameter you can tune to the extent you want. In time, d to the k to the o of k times polynomial in 1 over the smallest mixing weight. W min is the smallest mixing weight in the mixture, the input mixture that you have, and 1 over delta, the delta being the target accuracy. And so the way to interpret this result, because you're going to see more parameters very soon. So let me give you like some helpful parameter settings to keep in mind. You should think of k as a constant. I mean, I'll try to be more or less explicit about the dependence on k, but if you want to feel better about the kind of bounds I'm going to show you, it's good to think of k as a constant. Think of d, the dimensionality of the problem, as going to infinity. So we are really interested in optimizing the dependence on d. And in some sense, without loss of generality, you can assume that the minimum weight is at least around delta, because if it's smaller than delta, then you can essentially ignore because you're okay with some delta total variation error. Now, really, the Moitra Valiant result is about the parameter estimation guarantees. But, as I said, I won't distinguish between the two problems, at least in the beginning of the talk. Good. So that's basically done. And so why am I giving this talk? Well, because, we are going to ask this question, which is rather natural if you think about it, which is that how strongly are we using our modeling assumptions? What if, for example, the input data was not generated from a mixture of k Gaussian, but from like a close by model? What if the model was misspecified? Or, what if, for example, there were some adversarial constant fraction of outliers introduced into the sample that you are given? You can ask what would happen to our algorithms. And in fact, this question and this whole line of work on answering this question was begun in statistics by people like Tukey and Huber, which led to this whole area of work on robust statistics. And basically, we are asking a computationally efficient version of the kind of questions that Tukey and Huber were asking today. So more precisely, our goal would be to look at this twisted version of the problem where the input is going to be from a model, which is mixture of k, not quite mixture of k Gaussians, but something which is epsilon close in total variation distance to it. And up to that constraint, it could be an arbitrary distribution. So you can either think of this model as the input model being misspecified in the sense that you didn't quite get an IID sample from the model you were promised. Or you can think of this as taking samples and then introducing some epsilon fraction outliers in it. Okay. And the goal would be exactly the same as before, to compute a Gaussian mixture, which is close in total variation distance to the input mixture, except that this time, because your input itself is like epsilon far, from some correct model, you can't quite hope to get an error which is tinier than epsilon. And so our goal would be, getting some epsilon to some fixed function of k, which I'm going to call a poly epsilon in this talk error. Okay. And of course, we would like to stay as close as possible to the guarantees of the Moitra Valiant theorem that we just said. So, we would like to be polynomial in all the parameters of, the input model. Okay. That's the question we are interested in today. And so, even before beginning to ask this question, this rather looks like the question I began with in the first slide of the talk. So you should ask, well, what happens to these algorithms that were designed not keeping outliers in mind? Okay. So of course, it's unreasonable of me to ask them to handle this setting when they were not designed to handle it, but you can ask how robust or how resilient are these algorithms to outliers? And it turns out that, well, plainly speaking, they don't really handle outliers, but even if you were to modify them, it seems like there are like some bottlenecks in handling any fraction of outliers which is like larger than some fixed inverse polynomial in the dimension. Okay, and this is not an isolated phenomenon, to be honest. This is in some sense a starting observation in this whole area of robust statistics, algorithmic robust statistics, which is that the algorithms that we design to estimate various statistical models do not really handle a fraction of outliers which are a fixed constant with respect to dimension. Typically they can only handle inverse polynomial at best. Okay, and so that's the motivating question. And in fact, it was the motivating question even at the beginning, to be honest, in this whole algorithmic robust statistics. The recent wave which began with these two pioneering works. At some point, Santosh told me that he wanted to learn KGMMs in this Lyra of Impala paper, and he couldn't. So he started looking at k=1 case and tried to learn a single Gaussian, which turned out to be quite non-trivial. And that's basically the problem that these two pioneering works resolved. So so eventually it was pointed out as a key challenge in this research vignette that Elias and Santosh and David Woodruff wrote. And the main message of this talk is that basically that challenge is now resolved. Okay, so let me tell you this result that basically resolves this key open question. So let me, so these are basically the parameters of our result. So let me describe and let me go over them quite slowly. So we're going to get a epsilon robust proper learning algorithm. Okay, all the algorithms I'm going to talk about today are going to be polynomial in the number of samples they get. So it's, poly n is maybe not that big a deal, but that's what it means. Poly n is the number of samples. We're going to be able to handle constant fraction of outliers, just like we wanted. The running time, actually the sample complexity would be d to the O of k times some fixed polynomial function of 1 over epsilon. Now, what's nice is that this d to the O of k up to some constant in the exponent is essentially unimprovable. There are, evidence in the form of statistical query lower bounds that suggest that this is a dependence that is required in any algorithm that solves this problem, even non-robustly, to be honest. And there's also some recent evidence based on this continuous analog of the LWE problem that suggests that such a dependence might actually be necessary. So the dependence on 1 over epsilon, the polynomial 1 over epsilon, it's not clear what polynomial you could get here, but at least if you think of k as a constant, then the exponent of this polynomial in 1 over epsilon is some fixed constant depending on k. The key point, of course, is that we are going to be able to handle arbitrary Gaussian mixture models, meaning the components are completely arbitrary Gaussians. There may not be any separation between them. The parameters could be arbitrary, and the weights could be arbitrary, etc. So, basically, in some sense, this is as general as the problem could get in this setting. And finally, the error we are going to get is going to be constant if you think of epsilon as a constant. But let me point out that this is actually suboptimal. In general, we should hope for a polynomial in epsilon error. By polynomial in epsilon, I mean epsilon to the c sub k, where c sub k is some constant depends on only k. Okay, so it gives us a constant error guarantee, but the recovery guarantee, the error guarantee is exponentially weaker in the statement, from what one would like. And so again, to interpret this result, I'll point out these helpful parameter settings where you should think of k as a constant, again, for psychological benefits, d going to infinity. And again, just like in the previous argument I gave you, W min, really has to be about epsilon without loss of generality, the minimum possible weight. Is there a question, Eric, in the chat?
Yeah, actually, Sam Hopkins is asking whether this result is beating the Moitra valiant bound in the non-robust setting.
Excellent question. I'm about to come to it in a slide. Yeah, give me a slide. All right. So, so that's the result. And, as so often happens in TCS, there was basically an independent and concurrent work, which Ankur is going to talk about in much more detail, by Alan Liu and Ankur, which basically, also gets a result on the same problem. And let me explain the result as I understand it. So they also, are able to handle a constant fraction of outliers. So it's an epsilon robust algorithm, but their guarantees are in the stronger parameter estimation world. So they're going to be able to, get estimates of the parameters where, each component is close in total variation distance rather than just a mixture. Under the assumption that every pair of Gaussians in the input mixture is separated by at least some fixed constant depending only on k. Now, information theoretically in the parameter estimation world, you need some separation, and the separation that you need in this setting, information theoretically speaking, is some polynomial in epsilon. So epsilon to some constant depending on k. And under some slightly stronger assumption, this algorithm actually works. The sample complexity of this algorithm is going to be a polynomial if you assume that the minimum weight is at least some fixed function of k. And so, in general, there is some exponential dependence on some function depending on 1 over W min. So, if you think of that as at least 1 over some fixed function of k, then it's a polynomial time algorithm for any fixed k. And similarly with the error guarantee. So that's what happened, in maybe like a few months ago. And then, let me tell you a little bit about what happens hence and answer Sam's question. So it turns out that, we can actually improve a subroutine in our algorithm. I'll tell you about what this subroutine is actually later on in this talk. So it turns out that there is a certain brute force or epsilon net search that we were doing. And if you replace it with a slightly smarter algorithm, it turns out that we can actually get, a polynomial in epsilon error guarantees. So that at least, gets us what is, at least, if you don't distinguish between various polynomials, and at least it gets the right polynomial error guarantee in epsilon. And with that, it's actually true that, we get a better algorithm even in the noise-free or outlier-free setting than Moitra-Valiant's guarantee, which is in some sense, it's always been true that designing robust algorithms requires you to come up with truly new algorithms in some sense, but it's somehow pleasing to see that you can at least give like a new statement or new counterpoint to even classical results such as this. So the two key components behind this algorithm, which I'm going to try to explain to you in this talk, are a new partial clustering algorithm, and I'll explain to you how it uses sum of squares, etc., and a new tensor decomposition algorithm, which actually works without any assumptions on the parameters. And actually, it gives weaker guarantees, which in some sense are necessary. And so in some sense, these are the two main primitives that go into making this result happen. And in some sense, I'll try to give you a little bit of overview of both these components in
So I should
the talk.
clarify, I think. So this is for proper learning. So actually, one of the main bottlenecks in the D to the K to the K is actually for doing parameter learning. Because the issue is that, you need the smallest component, like let's say there's a parallel pancakes example. They need to be so close that they're actually statistically indistinguishable to the algorithm that would otherwise learn K-1 components. So the tower actually comes that way.
I see. So let me, so that actually makes sense. I think I mentioned it earlier. Let me also clarify again that the guarantees of Moitra-Valiant are in the stronger parameter estimation world, even though I am interpreting it only the proper learning world in order to, not distinguish between the two kinds of problems, but that's an absolutely good comment to have in mind. Talking more about this parameter estimation problem, which I'm not going to stress too much on, but just to tell you what happens here. So it turns out that we can use this very nice lemma that Ankur and Alan proved, for their version, and use it to actually get, in some sense, parameter estimation whenever possible kind of guarantee. So in general, parameter estimation is not going to be possible if all the pairs of components in your input mixture are not separated. And so what we can prove is that in some sense, to the extent that they are separated, we can actually recover it. So in some sense, it turns out that the input mixture can be separated into some K prime groups, such that in each group, basically the Gaussians are very, very close to each other. Then the output mixture, by the same algorithm that I told you on the previous slide, has the property that it also can be grouped into K prime groups, such that the corresponding groups are all close to each other. And the corresponding weights, total weights are all close to each other, etc. So in some sense, you can think of this result as saying that you get parameter estimation guarantees whenever possible. And so one corollary is that with this new lemma, we can actually improve the parameter estimation result. Of course, it builds on the school lemma of Alan and Ankur, but you can actually get it working under the assumption that the mixtures, the components of the mixture are only like some poly epsilon separated instead of some fixed constant. Okay, so if there were too many parameters for you, let me summarize the result like this. So together, these two works basically give you a fully polynomial, robust proper learning and robust parameter estimation algorithms for arbitrary mixtures of K-Gaussians. Okay, and so that's the result. And if there are any questions about the result, maybe I can take them now and then tell you a little bit more about how it works.
Hi, can you hear me?
Yeah.
Hi, sorry, I think I'm a little bit confused how this is different from the very first theorem you showed, the Moitra-Valiant theorem. How are these two theorems different from that one?
The Moitra-Valiant theorem is about algorithms that work when you are given an IID sample from a mixture of K-Gaussian model. These theorems are basically making them robust in the sense that they work even when you are given samples from a model which is only epsilon close in total variation distance to the mixture of K-Gaussians, and here epsilon is a fixed constant. So you should think of this as like a setting where, let's say, you were given an IID sample before, but that's not what you got as input. Instead, some adversary got in the middle and like replaced an epsilon fraction of the samples by completely adversarial outliers. And think of that setting, and basically these algorithms are saying that even when you have this noisy outlier-ridden data, you can actually get similar guarantees.
Thanks a lot.
Okay. All right. So what I want to do now is like tell you a little bit about how this result works. And so let me start by telling you these two components that I was talking about, and let me tell you how they fit together. So the first component that I talked about earlier was this algorithm that gives a robust partial clustering method. Okay, and so let me tell you what that means. Okay, so if you're given a mixture, the robust partial clustering algorithm is supposed to take the sample, take the corrupted sample from the mixture, and break it up into subgroups so that each subgroup basically looks like a corrupted sample from some submixture. The submixtures corresponding to different subgroups are basically disjoint in the sense that they are different components. And if you take any pair of Gaussians from different submixtures, then they are well separated. Okay. So what does well separated mean? So we say that two Gaussians are well separated if basically, you look at a point from one Gaussian and you're pretty certain that it's from one and not the other. So in other words, basically points from one Gaussian cannot pretend to be points, except with like some very tiny probability, they cannot pretend to be points from the other Gaussian. So formally speaking, what this means is that the total variation distance or statistical distance between the two Gaussians is, 1 minus delta sub k for some function delta sub k that goes to 0 as, k goes to infinity. Okay. So, so the goal of this robust partial clustering step is to take a partially clusterable mixture, which basically means that, it's a mixture where there are a pair of components which are well separated, and come up with a way to split the sample into two parts so that, the separated pair of components are on the opposite sides. Okay, so that's what I mean by partial clustering. And that's the first subroutine. And so what our algorithm does is like does this robust partial clustering step. And then once you have blobs which consist of components which are all somewhat overlapping in the sense that they are non-clusterable, then our result is going to apply this tensor decomposition with list recovery guarantees in order to learn these non-clusterable blobs. Okay, so at a very high level, algorithm basically can be thought of as doing this two steps. Okay, there's a lot of chat messages. Are there any questions for me? Sorry, I'm not able to look at the chat, so I'm just like asking.
These are questions that were answered, I guess, subsequently to them being raised, so it's all good. Okay,
perfect, excellent. All right, so all right, good. So let me tell you a little bit more about this partial clustering business, and before that, let me apologize for my diagrams. So like somehow when you think of two Gaussians which are well separated, a natural way to draw them is as ellipses. Which are non-overlapping. But it turns out that that's not quite the geometry of well-separated Gaussians. It turns out that, Gaussians can be well-separated even when their, associated ellipses actually can, in fact, for example, be completely contained inside each other. Okay. So let me tell you a little bit about, what the geometry of, well-separatedness looks like. And so this is a rather elementary lemma, but these independent works on clustering that arose last year basically established it. They proved that two Gaussians are well separated if the geometry of the two Gaussians satisfies one of the following three shapes. Okay, the first one is what you are intuitively likely to guess what separation should mean, which is the kind of diagrams I was drawing on the previous slide, and it corresponds to centers of the ellipses being far away compared to the extent of the ellipse in that direction. So basically what this means is that the distance between the two means is larger than the sum of the variances of the two Gaussians along the line joining the means. Okay, And so that's what, is the mean separated case. But it turns out that, two Gaussians can actually be, well separated even without, their means being close, means being far away. In fact, their means can be exactly equal, and then even then they can be separated, and in the following two ways. So the first way is the so-called spectral separation, which means that there is a direction, let's say V, such that if you compute the variances of the two Gaussians in direction V, then they are multiplicatively different. Okay, and in particular, one non-trivial issue with like this multiplicative difference is that both the variances can be really, really tiny, but they can still be multiplicatively very different from each other. And what happens is that in this case, the total variation distance between two Gaussians is still high. So you're still supposed to be able to, for example, tell apart points of one Gaussian from the other. And finally, the third way that they can be different is the so-called relative Robinius distance, which is in some sense a truly high-dimensional way that two Gaussians can be, well separated. And so in some sense, in this case, what happens is that in any single direction, the difference between the two Gaussians is very tiny. So for example, in this case, the example that I have over here, the two variances in any direction are basically within 1 minus some O of 1 over root D of each other. So, as D goes to infinity, this is basically the same. But somehow the aggregate of it really affects the total variation distance. And, they are still basically completely, you can completely tell apart, between points from one Gaussian and the other. Good. So the point of the slide is to tell you that, when you're trying to do this partial clustering step, you basically have to handle all the three kinds of separation that could arise between, components of your Gaussian mixture. And so, in some sense, one of the cool success stories in this robust statistics area is how basically the methods evolved to handle each of these three separation, each of these three different geometric ways of, separation that Gaussian mixtures can satisfy. And so what I want to do is like tell you a little bit about this history and then, be back on track. So as I told you, like basically this pioneering works on robust statistics, the two pioneering works, they began by, inventing this idea of outlier filters, among others, to do mean and covariance estimation of, distributions under some assumptions. And a little bit after that, a bunch of works came up with this sum of squares framework to attack problems in robust statistics. And one cool idea that this framework, used was this idea of certifiable sub Gaussianity. So I'm going to be really kind of hand wavy in this part. I apologize, but I don't have enough time to tell you much in detail here. But the message of this, idea of certifiable sub Gaussianity and certifiable anything is that it's some algorithmic way to utilize some analytical properties of distributions. One upshot of this line of work was that, it gave us methods to handle separated Gaussian mixtures in the first kind of way. So, remember those mean separated blobs? Well, those are the kind of mixtures you can actually cluster if, you use this idea of certifiable sub Gaussianity. But the other two were still, somehow mysteries. We didn't know how to do them. And the next key idea that basically, made progress on this was this idea of certifiable anti-concentration, which, two independent works actually came up with. And it was applied on this problem of list decodable regression, which if at the end there is time, I'll tell you a little bit about how can we view it as like a very special case of the problem we are looking at, where spectral separation really plays a role. And finally, for handling Frobenius separation, we needed this new idea of certifiable hypercontractivity of degree 2 polynomials. And with these three ideas, the sum of squares framework was basically ready to handle clustering of all non-spherical mixtures of Gaussians. And that's what these two independent works basically proved last year. And that's basically our starting point for this robust partial clustering algorithm. Basically, what this works proved is that there is a robust algorithm for clustering non-spherical mixtures of Gaussians that basically succeeds in polynomial time if k is a constant, but the running time is d to the k to the o of k. In fact, other than the running time, there are like two other issues that we need to resolve with this work. One is that, we only handle equiweighted mixtures, meaning all the weights are equal to 1 over k. We need arbitrary weights. And they only handle, the mixtures where every pair is well separated. In our setting, we only have this partial clusterability guarantee, so we can't quite, apply this algorithm as a black box. And of course, if you remember, the kind of guarantee I was telling you earlier was d to the o of k time. So, the running time, of course, is also too slow for the kind of theorem that we are shooting for.
Pravesh, can I put in a quick question from the audience?
Sure, yeah.
Right, so there's a question about classifying points. So what if instead of actually, figuring out these different clusters, you want to just say for a point as it's revealed to you, does it belong to this cluster or that cluster? Is this problem, what's known for this, I guess, is generally the question from the audience.
Is that the clustering problem in some streaming setting or something? Is that the question? Or like online version of the problem? Like, what's the difference again? Maybe I didn't catch it.
Amireza, maybe I suggest you unmute yourself and make this a little more interactive.
I think it's asking, what if I don't want to learn DTV? I just want to know which sample come from which Gaussian.
It's actually, in some sense, in fact, I don't think I know a way which can do one but not the other. In some sense, if you can essentially cluster, then you can also learn them well up to total variation error. So at least I don't see how the relaxation would help at all, algorithmically speaking.
Got it. Okay, there's some extra discussion in the chat, so we'll take it offline.
Okay. All right, good. So then I can tell you like the upgraded version of the clustering guarantee that we need in this work. And so what we show is that we can build on these ideas to get a partial clustering algorithm that again succeeds robustly. Yeah, I guess that's a typo there. I don't need well-separated mixtures. I only need partially clusterable mixtures. That's the point of the theorem. And this theorem handles arbitrary weights. So it upgrades the guarantees from the previous theorem in two ways. It handles arbitrary weights and it handles partially clusterable mixtures. But notice that the running time is actually not the kind of running time we are happy with. It actually gives a decent guarantee when W min is lower bounded by some fixed function of k. But we are shooting for d to the O of k kind of guarantee. So this is not going to be good enough for us. And I'll show you how to modify this very soon. But I'll stick to this version for a second. Okay. So that's the partial clustering part, or at least what I'll tell you about it right now. And so, let's now go on to the second component of how to deal with each of these non-clusterable blobs which result from applying the robust partial clustering step. Okay. So the idea is actually, in some sense, the classical idea, in some sense, the idea that even Pearson had like more than 100 years ago, which is this use of higher moments of the mixture to somehow infer properties of the component Gaussians. Okay. And so to explain this idea, let me take a very simple example to tell you what's going on. Okay. Let's look at the case when all the covariances are identity. Okay. And the means are different. Okay. Then here's an observation. And let's also imagine that there are no outliers, okay, just to clarify this idea to us. So in this setting, if you compute the empirical third moment of data, that's what the sum xi to the tensor 3 averaged over the n samples means. So if you compute the empirical third moment, it basically looks like a third order tensor, so d by d by d tensor with components mu i's plus some junk that you can basically remove, okay? So ignore the junk. So essentially what this means is that, by computing third moment of the data along with second moments, you can basically get access to this first term on the right-hand side. So you can get basically a tensor whose components are mu1 through mu k, okay? Now, that's great. In fact, it's very useful. In this very nice line of work, begin with this work of Su and Kakade, what they showed was that, in particular, by looking at this assumption, looking at this, idea, if you further assume that mu i's are linearly independent, and in fact, they have some bounded condition number, then in fact, you can use algorithms for third order tensor decomposition to learn the means and therefore, solve the problem. Okay. So that's a great idea, except that in our case, we've got to handle outliers. In fact, that's relatively simple in the sense that we'll rely on all this technology that has been developed for 4 years and use robust estimation algorithms to estimate these tensors robustly. The more non-trivial part is what to do with the fact that, our means may not even be linearly independent and forget condition number, etc. Okay, so what to do with that? And so here's the key idea, okay? The key idea is that we can still learn a k-dimensional subspace that contains all the means. We may not be able to tell what the means are, but we can tell what is the k-dimensional subspace that contains it. That's good. And that's probably not even that hard to imagine. Now, imagine that by some fiat, I declare to you that, hey, you know what? All the means also happen to be small in norm. Okay, so I give it to you that, all the means are like some absolute constant, in L2 norm. Then what you can do is take a L2 ball in this k-dimensional space, get like a fine enough epsilon net of it. In fact, you can show that, the fineness really only depends on like some polynomial depends on the epsilon. And so all in all, you basically get like, list of candidate mean vectors. List itself is of size polynomial in 1 over epsilon, where the exponent depends only on k. Okay, that's great. So now you have a small list, so you can just take k tuples of candidates from here and run some off-the-shelf statistical checker. Just check if the hypothesis is closed on, let's say, like by taking a fresh sample. And I'll ignore the details like this because they are relatively standard and can be worked out. But that's the idea. Okay, that's if in addition you had this assumption, you'll be done. Okay. Of course, where would this assumption come from? And that's where the partial clustering step really helps. So what you can show is that if you partially clustered a mixture, so in other words, you have a non-clusterable blob in front of you, and you do something called as putting in isotropic position. So basically, you compute the covariance of the mixture and basically do some linear transformation on it. Again, ignore the details, doesn't matter. You can basically make this condition hold. That's the point. Okay. So that's awesome, right? Like, so we resolve the case of spherical mixtures at the very least. And let's now see, how this idea can actually be generalized to, more general mixtures. And so here is where, this observation that Daniel Kane made in his, paper that basically is a direct starting point of this work, actually. So Daniel Kane basically resolved the case of learning, robustly learning mixtures of two equiweighted Gaussians. Okay, so mixtures of two Gaussians where both the weights are half. And here is the key observation he makes. There is a certain, variant of forth moments that you can compute from data in the mixture. Let's call them Hermite moments. I'm not going to describe to you what those are. And what he observes is that this gives you access to an object, let's call it T sub 4, which looks like the following. It's some weighted combination of sigma I minus identity tensored with sigma I minus identity. So it's a fourth moment, it's computed from fourth moments. And so you can see at least the dimensions roughly match. Sigma I minus identity is a D by D matrix. So, this is basically an object of D by D by D by D size. And the sim is basically, some average over permutations of the 4 modes of the tensor. And again, if it's hard to visualize, I'll say, don't worry too much about it. But basically, one of the terms in this symmetrization is really truly sigma I minus identity tensored with itself. And there are like 2 more terms, which are like, in some sense, permuted versions of this, and we don't quite like them. Okay. So now, if you were to dream, you could say, hey, if I had not T4, but some version of this, which is T6, and, there was no sim, and sigma I minus identities were linearly independent, blah, 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 then we could run tensor decomposition just like Su and Kakade. But, we have none of those wish lists. Instead, here is what, Daniel observes in his paper. He observes that there is an operation you can do on this object T sub 4. I'm not going to describe this operation in too much detail, but it's some random contraction operation that takes a D by D by D by D tensor and produces D by D matrix. And the matrix looks like basically a linear combination of sigma I minus identity, in fact, a convex combination, plus some error term E. And here's the key observation about the error term, that the error term is actually a low rank matrix. It's a matrix of rank order k square. And again, if k is a constant, this is a constant rank matrix. Okay. So why is this observation useful? Well, our idea is going to be to learn covariances using this trick, or at least learn the subspace of the covariances up to some low rank error. Okay. And so what this paper of Daniel Kane did was basically actually accomplish this for mixtures of two Gaussians. We are using some ad hoc structure in this T4, which arises only in the case of k equals 2. In our case, we have to do a little bit more work. What we show is that if you take some polynomial in k many random contractions, this transformations that I spoke on the previous slide, then you can show that the subspace spanned by this poly k different objects contains all of the sigma I minus identities. Okay, just roughly speaking arises because you can use some relatively subtle LP duality argument to show that you can cancel out these low rank errors. Okay, again, if that didn't make sense, forget about it, because the key message is that just like in the mean separated case, you can get a constant dimensional subspace that contains everything your heart desires. Okay, so that's great. And so, that basically leads to, that's all I'm going to tell you about it. So this leads to this list recovery theorem for tensor decomposition, which says that, if you have a similar upper bound on the norms of mu i's and sigma I minus identity, again, we can ensure that by clustering plus isotropic position, then we can find a subspace. And this time the subspace is going to be of dimension, 1 over epsilon to some exponent that depends on k, that contains good estimates of mu i's and sigma i's. Okay. Now, Remember, I told you that our earlier guarantee was exponentially weaker. That was because what we were doing at this point was just build an epsilon net of this subspace. And because the dimension of the subspace is like polynomial in 1 over epsilon, the epsilon net itself would be exponential in the dimension. And so that's what resulted in the weaker guarantee. And so, but we realized that what we can do is just do a slightly smarter algorithm where we don't actually do a brute force search over an epsilon net. A slightly smarter algorithm here actually, basically works. And we can, in fact, get not a exponential in the dimension, but a polynomial in the dimension size list of candidate parameters. Okay, so that's great. Those are the two components. I told you everything I've got. And so, those are the two components that we just discussed. Remember that partial clustering guarantee is still weak. But if you put these two together, with, in some sense, the obvious algorithm that you will do, to like do clustering and, put it in isotropic position, then apply tensor decomposition to each blob and like check the candidate hypothesis, it immediately gets you, this kind of an algorithm where the exponent of D is, is a function of the inverse minimum weight. Okay. So in like, 2 minutes, how we can actually improve it to, fully polynomial guarantee. I'll be somewhat sketchy, but, it's more or less, similar to what we were doing already with like one key idea. And the key observation is that the clustering algorithm spends an exponential amount of effort or running time or sample complexity in the inverse minimum weight entirely because of trying to handle the spectral separation case. So remember that multiplicative difference in variance I talked about earlier? Well, that's the case that really hurts the algorithm's performance. So what do? We say, well, okay, punt on it. Let's not do it. Let's just come up with an algorithm that handles partially clusterable mixtures only in the relative Robinius sense. Okay. That's great. It turns out that in this case, we can actually come up with a D to the O of 1 times some polynomial in 1 over epsilon guarantee. So that's great. Like we succeeded now. But of course, we really kicked the can down the road. We've handled spectral separation somewhere. So I'm going to be somewhat sketchy about this, but the key idea is the following. That, we basically run the tensor decomposition process that I told you in the previous slide. And now, we generate candidates. All of this essentially works as is. Except that once we come up with the candidates, the candidate mixtures could have, a direction along which a pair of components in the candidate mixture are spectrally separated. So what we do is we only look at the spectral separation when we are trying to prune away the candidates. Okay, so basically, if we realize that in one of the candidates there is a spectral separation along some direction, we basically try to cluster the data in that direction. Okay. So in some sense, this trick of like, not letting the partial clustering method do the hard job and instead do the hard spectral separation only on the candidates is what saves us, this exponential dependence on the minimum weight. That's it. That's all I'm actually going to tell you about. And so, to summarize, these two results basically give together a fully polynomial, both robust proper learning and parameter estimation algorithm for arbitrary Gaussian mixtures. And, beyond the theorem, the key observation is, how like different techniques, in some sense came together along with like collaborations to actually resolve this question. So, somewhat cheesy, but, I think it's neither the first nor the last success story of collaborations in TCS, but it's certainly a good one. All right, so lots of nice further directions, but two obvious ones, which is, how do you go beyond Gaussian mixtures? And ask me about it if you want to, maybe hear my thoughts on that. But another thing is that, the algorithms in some sense give evidence that, polynomial bounds and all these parameters is possible even in the robustness constraints. But of course, the algorithms are really, really impractical. And so, it's a natural question to ask, how do you build more practical algorithms? All right, that's all I've got.
Thanks, Pravesh. If you go back to the question slide, I actually have a little bit of a follow-up. So I guess the dependence on a dimension and k you had mentioned is in some sense optimal. So what would you hope for a more practical algorithm to give?
Practical is essentially code for don't do SOS first. Okay, so in some sense you want to replace this SDP solving procedures with slightly simpler algorithms. And it turns out that there is some hope that you can replace them by, let's say, simpler spectral algorithms, which might be a tad faster in practice. There are also, I think, bottlenecks in this tensor decomposition procedure, it's really doing like if you actually open up and look at the dependence on k that arises, for example, horrendous functions like superfactorials in k arise. And superfactorial is basically, square of the factorial of k, for example. These are the exponents that arise very naturally in the setting. And so, the question is, even under some additional assumptions, can you actually get some relatively tame dependence on this parameters k? Because then, it would improve both performance and the running time guarantees.
Got it. So the improvement here would be in 1 over epsilon, right?
Sorry, I guess I didn't.
So sorry, just before Ankur chimes in. So what you're saying is an improvement in the poly 1 over epsilon, right?
Yeah, I mean, so the exponent of 1 over epsilon in the running time is actually pretty bad in the sense that it's, I think it's square of k factorial. And so, if you want to call k a constant and feel good about it, which I do, it's fine. But, if you want a practical algorithm, you certainly have to, perhaps under additional assumptions, try to hope to improve that.
So I think there's another silver bullet here too, which is if you smooth the mixture, then all of this might go away.
That's an excellent point. Yeah, I should in fact have mentioned. In fact, there is a version of tensor decomposition that you can do even for arbitrary covariance Gaussians, and it was actually invented in this paper of Rong Ge, Sham Kakare, and Qing Huang.
Qing.
Yeah, yep. Exactly. It's a really fun paper, and it can handle, it gives a fully polynomial guarantee for not just, I think, I remember they can handle like up to some square root dimension number of components. And so in some sense, this Su Kakare work already showed that there is some, benefit in making assumptions on the parameters. And under those assumptions, you can really get away with, much faster running times. And yeah, so that's definitely a silver bullet, as Ankur says. It might actually be pretty reasonable in practice, for example, in some setting, to assume that the parameters of the mixture that you have are smoothed in some sense.
Let's see, so Sam is patiently waiting his turn, so I think maybe I'll ask him to unmute himself.
Yeah, okay, I think this is just a version of the question of what you were just discussing, but do you have any wild conjectures for what the right class of GMMs that is learnable in poly dk time is? So, we know that under mean separation conditions, these papers from 2017-18 get you something interesting in d to the log k or poly dk. Right. Presumably, you should be able to go beyond just mean separation, but maybe not. I don't know. You can't, like parallel pancakes will kill you.
Right.
What should be the right class of GMMs in between?
It's an interesting question. And I guess maybe my hope was a little bit tamer. Like what you are worried about is the exponential dependence on k, but I guess I was going to be okay with a singly exponential dependence on k and not have factorials in k floating around. So, it's true that I don't have ideas, like smoothed analysis is clearly one model, but I can't think of like another natural model where you could hope to beat singly exponential dependence in k. But at the very least, you could hope to improve this weird polynomials, in 1 over epsilon that arise. They might be constants, but they're likely, not that great if you want to run algorithms.
Right, so if there's no more questions now, I guess we'll bring up Pravesh for more questions after the second part of the double feature. So I'll ask Pravesh to stop sharing his screen and Ankur to start sharing his. All right, so for the second part of this double feature, we have Ankur Moitra, who's going to tell us about the second paper that Pravesh kept alluding to. So Ankur, take it away.
Great, thanks for inviting the both of us. So excited to tell you about some work with Alan Liu. So Alan's a first-year grad student at MIT. And, in some sense, I've been thinking about these kinds of problems for a long time, off and on. So it's really nice to see, not one, but two solutions to these things, assembling a lot of tools that I know and love. So that's kind of cool. As Pravesh mentioned, actually, when we first started thinking about algorithmic robust statistics, I think everyone had this idea, let's study mixtures of Gaussians. And it took me a while to realize maybe I shouldn't be looking for a problem that's non-trivial on the learning axis and open on the robustness axis. And that's why we studied things like a single Gaussian, because no one in their right mind would ask, can you learn a Gaussian without noise? But you can ask whether you can learn it with noise. And personally, every time I gave one of those talks, there was a lot of excitement in the audience. People seemed to really gravitate towards these ideas. But inevitably in the question section, someone would always ask me, what about mixtures of Gaussians? It's like, as I said in the abstract, the problem had a target on its back, or I had a target on my back when I was giving talks. So I'm glad that we can at least, put a fairly decisive nail in this thing, although there are more assumptions that go into these works. I'll tell you a bit more about them. So I'm not going to give you the complete full statements. I think Pravesh did an awesome job. Actually, in my talk, I'm going to focus on how to think about different learning goals, how they relate to each other, and these new techniques that I think make these kinds of things possible, at least on our end, and they're pretty different than the ones that Pravesh will tell you. And I welcome the audience to try and figure out how to map between the two, because it's an open question. So the basic result is that there's a polytime algorithm for robustly learning mixtures of any constant number of Gaussians. The critical thing is that it's in high dimensions and that you get a dimension-independent robustness guarantee. But moreover, we get a polynomial dependence on the corruption rate. So if epsilon is the fraction of things that are corrupted, then we get some epsilon to the omega of 1, where that constant depends on k, guarantees for how close we learn the thing on a component by component basis. Now we need some assumptions on the mixing weight, as Pravesh alluded to. So we need things like bounded fractionality. We need upper and lower bounds. Any polynomials will suffice on the covariances, and you need some TV distance lower bounds between the components. But one thing I do want to emphasize, the part that I'm going to tell you is going to have to do with generating functions. And actually that part of the argument is going to work without these kinds of assumptions. It's really a question of putting some of the different tools together in the literature. So I sort of do believe that a lot of these assumptions could be removed by, referring to other works, but, this certainly is a caveat with the things that we're saying right now. There's another paper that I'm not going to tell you about, but with Alan, we also got some other kind of improvement where what we gave optimal dependence on the corruption rate, in the sense that you have epsilon fraction of corruptions, and we get O tilde of epsilon closeness, where there's no dependence on k for that. But it's not for the proper learning problem, and it's not for parameter learning, because this type of guarantee is impossible here. It's for the improper version, and I'll explain the sort of zoo of learning results later. But roughly the relaxation is we spit out a polynomial mixture of Gaussians, where instead of mixing weights, we have polynomials in front of the components. So I'm not going to talk about that result, but first what I want to do is I just want to set the stage, because for a lot of us who think about theoretical learning, we use a lot of these terms like parameter learning, proper density estimation, improper learning, pretty fluidly, but they're very different problems. So let's make sure that we're on the same page. So the basic task in distribution learning, so in unsupervised learning, is you're given samples from an unknown distribution, but it lives in some known class. So for us, that will always be a mixture of k Gaussians for today. So we have k different components. The wi's are the mixing weights. The gi's are the high dimensional Gaussians. Now, when we get samples from this distribution, what does it mean to learn the distribution? Well, let me organize them in order of increasing difficulty. So there's improper density estimation, which is what I could do is my algorithm could spit out any density function or description of it, which has the property that it's close to the true density function in total variation distance. So it matches the distribution in a statistical sense, but you're relaxing the problem because you're allowed to spit out anything, even something that's not necessarily in the class. That's, for example, how we relax the mixing weights to be allowing polynomials instead of the mixing weights. And that second result I told you about. Now, there's also proper density estimation, which is where you want to output something that's really from the class. And then you want it to be close, again, as a distribution. And always in distribution learning, total variation distance is one of the most natural things you can ask for. And what I'll really be focusing on for today is something called parameter learning. So here, what you want to do is you actually want to estimate the true parameters of your model. So you want to spit out something that actually is a mixture of K-Gaussians, but you want to have the property that, you can never know which component is which, but for whatever model you spit out, there's a permutation of its components that matches them with the true components in the underlying mixture. And across that matching, you're close in some kind of norm or total variation distance. So it's a very strong kind of learning goal. And what's a little bit wild about something like parameter learning, that's something that the classic, things that we do in just non-robust learning usually aim for that stronger guarantee. But, it turns out that there are some basic questions you have to answer to solve something like parameter learning. And it's something that I think we're not as used to sort of bringing out when we talk about algorithms and these things. So I'd like to do that. And it's something called identifiability. It's really something that for me, I think makes a lot of these algorithms that solve parameter learning tick underneath. And it's one of the hardest questions you have to resolve en route to getting an algorithm. So let's focus on parameter learning. Well, if I can even hope to learn the parameters of my mixture of Gaussians, I better hope that it's identifiable in the following sense. What I need to hold is that for any two different mixtures, so any two candidate distributions from my model, they better have the property that if their parameters are different, so they don't match on a component by component basis exactly, then they at least better be different as distributions, because all I'm getting are samples from the distribution. So the way to think about this is that if this went wrong, then we couldn't actually solve parameter learning. Because for this pair of mixtures, we cannot learn them on a component by component basis just from the samples, regardless of algorithms and regardless of how many samples you're given, even with infinitely many samples. So if this condition holds, the model is called identifiable. So in fact, for mixtures of Gaussians, identifiability goes back a long ways. It goes back to the work of Teicher in the 60s, who showed that mixtures of Gaussians were identifiable. But they did it with something that's not good enough for our purposes, because what they do is they just go way out into the tails of the distribution, and they use those tails to read off the highest variance component, and then they recurse. And that's not good enough for us, because when we're looking for algorithms, we actually need a quantitative version of identifiability that's much stronger. That's called polynomial identifiability. So the way that this works is basically the same setup as before, but now with quantifiers in there with actual parameters. So if you give me two mixtures and their parameters are epsilon different. So, I'm going to be a little bit loose with this, but roughly what it means is that there's no matching across their components, so that across the matching, they're epsilon close in total variation distance, and their mixing weights are epsilon close. So if these two different mixtures have, are epsilon different, then they must also be noticeably different as distributions. So they need to at least be delta of epsilon far as distributions. So when we can take delta of epsilon to be a polynomial in epsilon, and in fact, we'll even throw in polynomial factors in the dimension too, then we say that the problem is polynomially identifiable. This has nothing to do with algorithms. This is a purely effective bounds question about a statistical problem. But what I claim is that, it's really a prerequisite for designing algorithms. If you give me an algorithm for learning a mixture of K-Gaussians in high dimensions that takes poly in 1 over epsilon samples and poly in D samples, then somewhere lurking within that proof is a proof of polynomial identifiability, because otherwise your algorithm could not work. And I think it took a long time for people to realize that this is maybe not just a byproduct of an algorithm, but maybe it's one of the key things that happens in the proof of the algorithm. So I think of it personally as really the key ingredient for parameter learning. And so what's known about polynomial identifiability for something like mixtures of Gaussians? Well, this goes back over a decade now, pretty crazy to say that. But in this joint work with Adam and Greg, we showed that mixtures of two Gaussians are polynomially identifiable from their first 6 moments. Now you need some conditions to make sure that the distribution is like an isotropic position, but I'm not going to go into all the assumptions because we'll really need a different version of identifiability anyways. But the rough way that this works is that even in one dimension, what does it mean for a mixture to be polynomially identifiable? It means you give me two different candidate mixtures. One of them has the blue components, the other one has the red components. And you take their two density functions. You can see that the blue and red components don't match. They're far on a component by component basis. And you take their two density functions and you pointwise subtract them. So the key thing that we proved is that if you look at that function you get from subtracting their density functions, it crosses the zero axis at most 6 times. And what that buys us is that you can fit a degree 6 polynomial to the sign difference. And that tells you that one of the first 6 moments between these two different mixtures is different. Now, it turns out that when you prove identifiability this way, by looking at correlation with low degree polynomials, rather than looking at the tails of a mixture, it actually paves the way towards getting stronger quantitative guarantees. And that's what we did. We used this idea of the first 6 moments and reasoned about the corresponding system of polynomial equations and its stability properties to prove some form of polynomial identifiability. And as Pravesh alluded to, the real problem is that in high dimensions, well, how do you solve the problem? Well, we solved it by reducing to a sequence of one-dimensional problems. And that's kind of just not the right way to do robust learning, in high dimensions. This reduction to one dimension is just not going to work. Because the issue is that, while you can do it for the non-robust learning, you can reduce to a sequence of 1D problems. The trouble is that on a typical one-dimensional projection, even the distance between the means is going to contract by a √D factor. And this inevitably incurs some polynomial factors in the dimension that show up in your quantitative guarantees. Or to put it another way, you have two Gaussians that are far in total variation distance from each other in a high dimensional sense, but not necessarily when you project them on a random one-dimensional direction. And there were extensions of this work to mixtures of K Gaussians, where the degree of the polynomial test functions depends on K. So really just to summarize what's going on, in the non-robust version for the learning results, what we have is that there's a polynomial relationship between two things. On the one hand, it's the total variation distance between the two different density functions of the two Gaussian mixture models. And on the other hand, it's some measure of their discrepancy in their first order K moments. Now, the catch is that these two sides, while they're polynomially related, they're polynomially related in a way that they lose dimension-dependent factors. And that's really the thing that goes wrong for robust learning, at least the way that I think about these things, because it's just not good enough. The way to think about it is when an adversary can corrupt some fraction of your samples, they really can move your moments. And if they can move your moments noticeably by something like an epsilon, then if you're losing poly and D factors when you go to the other side of this expression, that's just not a strong enough form of control on getting the right hypothesis. So the way that I think about these things is that, the first thing we needed to do in order to solve this, robust parameter learning problem for mixtures of K Gaussians was we better prove a way stronger form of identifiability. Not just identifiability in the limit in the way that it's used traditionally in statistics, not just in the form of polynomial identifiability as we use in a lot of theoretical machine learning, but maybe we need what I'll call robust identifiability, because we need a polynomial relationship between discrepancy in moments on the one side and TV distance in a component by component basis on the other. But we need to prune away all of the dimension-dependent factors to do this. And now reducing to a one-dimensional problem is just not going to work for us. We have to actually attack the high-dimensional problem directly. So we're going to do that, and it's kind of magical to me. I don't think there are any people from the usual undergrad class I teach, math for computer science, in the audience, but I feel kind of guilty. A few years ago, I decided generating functions were definitely not cool, so I removed them from the class. I think they have some quotes from me, about my views on generating functions. So I don't expect you to be in the audience, but if you are, my fault. I'll teach you generating functions next time. And eventually we're going to do this thing that I really hope I run out of time before I have to get to, which is called the sum of squares relaxation. It'd be great if I could get some like ominous music to play, but I couldn't figure it out. So let's all hope that you ask me a lot of questions and I don't get there. But I want to tell you about a technique that, to me is really beautiful. And in fact, I don't know how to wield it. So I think that's one of the really cool things is it's going to make a particular part of, this giant machine of how do you solve this robustly learning mixtures of K-Gaussians. It's going to make this particular part work in a really cool way where I, would love to see it be extended in other directions and applied to other kinds of problems. Because it seems like a cool way to directly attack a high dimensional learning problem. So let's just roll up our sleeves and do it. So first, what I'm going to do is I'm going to start with a high dimensional Gaussian, just a single Gaussian. There's no mixtures right now. And it's going to have a mean mu, that's a d-dimensional vector. And I'm going to write its covariance in this funny way, where it'll be I plus sigma. And that's just a more notationally convenient way for what I'm about to do, to write the covariance matrix. And now I'm going to introduce a little bit of helpful notation. What I'm going to do is I'm going to think about formal variables, a vector of formal variables. We're in d dimensions. So I'm going to think about a vector x, which is x1 through xt. And I'm going to take this thing that I'm going to call mu of x, which is just the inner product between the vector of formal variables x and the mean mu. And I'm going to do the same thing for sigma. Remember, sigma is not the covariance. It's related to the covariance. And I'll take the quadratic form of x on sigma, and that's sigma of x. So what's going on here already, you can get a bit of intuition, is I'm not going to reduce to one dimensions because I'm going to use formal variables to express for me what happens along all one-dimensional projections simultaneously. And that's kind of what I'm trying to do here. So let me tell you the first lemma. This is the key lemma. And it turns out that if you write the right generating function in these formal variables x, so it's e to the mu x, and then I have this extra formal variable y, that's really just to help me do bookkeeping. Well, I can expand this generating function on the left-hand side, and it'll turn into a series expansion that has something to do with the moments of a Gaussian. So I haven't defined what hm of z comma x is. These are Hermite moment tensors, and I will not define it for you because I'm just going to show you how this works in one dimension instead. But the way to think about it is that what this really stores is if you plug in for the formal variables x, some vector v, it's going to tell you the Hermite moments on a particular 1D projection of that Gaussian. So let's not go there because a lot of the stuff you can still understand the shadow of what it's doing just in one dimension. So let's make our problem simpler. Let's say we have a 1D Gaussian. So we've gone from mixtures of K-Gaussians to one Gaussian. We've gone from high dimensions to one dimension. And now we can actually do something. So we have a mean mu and we have the same parameterization. Its variance is 1 plus sigma squared. And I'll call it lemma 0. I can take the same type of generating function. There are no more x's. There's only the formal variable y that's doing my bookkeeping. And what I claim is that the same type of expression holds, that the series expansion will have something to do with useful moments. I still haven't told you what hm is, but it'll fall out from the proof. So all we do is we apply Taylor's theorem and we expand the left-hand side. And if you expand it, you'll just be taking powers of whatever is happening in the exponent. But really the more useful thing to do is to collect the terms that are in front of the different powers of y. So I've done the algebra for you. And now things are going to start to look at least reasonable and interesting and familiar. Because what these are related now to the moments of a Gaussian. So let's just look at one term here. So what's the term in front of y squared? Forget the 2 because that's this 1 over m factorial in the expansion. The important thing is the mu squared plus sigma squared. That looks like the second moment of a Gaussian. It's actually not quite the second moment because remember, my variance is 1 plus sigma squared. It's really the second moment minus 1. And that's exactly what that expression is. And that's what my lemma 0 is telling me, is that the moments show up as terms in the series expansion. Same thing happens for the other part. It's the expectation of z cubed minus 3z, where the expectation is over Gaussian variables from the Gaussian we started with. And if you work it out, these will be exactly what the Hermite polynomials are. So you can take this as your definition for the Hermite moments, is they're the things that come up in this series expansion. So that's the end of that proof. And now let's go back to mixtures, and let's make our problem a little bit harder again. Well, I claimed that this identity extends, at least the lemma 1 that I gave you, the high dimensional version. This extends in the obvious way to mixtures of k Gaussians, because all I do is I take mixtures of the generating functions. But now the nice thing is that when the terms in my expansion in lemma 1 to begin with were the moments of a single Gaussian, the Hermite moments, the multivariate Hermite moments, they now become the multivariate Hermite moments of the mixture. And that's very useful because, as Pravesh mentioned, in all of this stuff, moments of the distribution play a key role. So this is relating the moments on the series expansion to the parameters on the left-hand side of the mixture model we want to learn by storing them in a generating function. And so let's do exactly that, as I'm alluding to. Let's revisit identifiability. And let's study it in this language through generating functions. So what does identifiability look like redux? Well, the same type of thing. You give me two different mixtures, M and M prime. They have their components. I can form their two generating functions. These are formal expressions in the vector variables x and the formal variable y. What I want to show is that these two generating functions, if they're the same as formal expressions, I want to show that that's if and only if the parameters match on a component by component basis. And I'll prove that for you. We will give a full proof of this statement. In fact, what we're going to do is we're going to use differential operators to isolate a single component. So let's start with differential operators in 1D to make our lives simple. So let me guess the right differential operator. So let's look at this differential operator that takes the partial derivative with respect to y. Remember, that's one of our special variables. And then I'm going to subtract off, mu plus sigma squared y, so this linear function of y, times whatever I started with. And now we're in good shape. Because what happens when I apply this differential operator to the generating function for a single Gaussian, where its mean and variance match the corresponding parameters in my differential operator. So the mu's and the sigma squareds are the same. It kills it. Actually, it annihilates it. This is related to something called annihilating polynomials and differential operators. So this operator annihilates the component because when you apply the differential operator, you get 0. And this holds as a formal identity in y. Now, you might be wondering, how is this related to algorithms? This is an operator that I'm applying a differential operator. But what I claim is that this is really just a very convenient, slick way of doing a polynomial rearrangement on the series expansion. Because if I took the same differential operator and applied it to the right-hand side, not to the e to the term, but I applied it to the summation over m, I could apply this operator on a term-by-term basis, and it's just telling me how to rewrite the terms in my expression in a particular way, where the left-hand side tells us that it kills everything. And now what I claim is, let's start to pull back, the curtain here. This works in high dimensions too. No one said you have to do it in 1 dimension. So I can do a differential operator that applies the partial derivative with respect to y. and I subtract off this other function times the same generating function. But now I have x's in there because I'm working in d dimensions. Is that a big deal? You know, not so much. Again, you have this formal identity that it annihilates the generating function for that component, at least if I choose mu of x and sigma of x right. So now I'm on my way, but I want to emphasize that, you know, for me, we wouldn't have been able to do this if we had to actually write down these expressions, and I certainly wouldn't be able to fit them on slides, because we'd have these gargantuan expressions that are like complex multivariate polynomial rearrangements, and I would have no idea what sense to make of them. But now I think I understand it. And so, you know, working towards this goal of proving identifiability with the language of generating functions and differential operators, one of the questions you could wonder is, you know, so far I've told you the right differential operator annihilates the right component. But the trouble with a mixture is that we have more than one component. So what does this right differential operator do to the wrong components? Because those are hanging around too, like it or not. This turns out to be a bunch of simple lemmas too. It's nothing surprising. You know, what happens if I take the differential operator with mu of x and sigma of x in there, and I apply that differential operator d to the wrong component, one with mean mu prime and corresponding sigma prime instead? I'll get the same kind of thing, except for the fact that, you know, now I'll have a polynomial in front that looks at the difference in means and difference in sigmas. So in particular, when mu prime equals mu and sigma prime equals sigma, this is the same thing that I alluded to before. It annihilates the component. So this actually makes our life a bit more complicated, because when we apply this differential operator, you know, it kills the right component. Great. You apply it to the other components and it makes them more complicated, because now what's sitting in front of the generating function is not a mixing weight, but a polynomial. So the mixing weights become polynomials. Well, so be it. You know, we've embarked on this path. Let's see where it goes. So what happens, at least, if I then later apply the right operator, even if I have a polynomial sitting in front? What you can check is that all it'll do is it'll differentiate the polynomial in front with respect to y. And this is a pretty easy thing to think about, is because, you know, when you look at that linear expression that depends on the x's and the y's, that's going to multiply the component. You take the partial derivative, and, you know, you could apply the partial to p, or you could apply it to the exponential. When you apply it to the exponential, it cancels out with the other part, and all you have left over is what you do in front. So this is great, because even if I mess up my mixture by making the mixing weights polynomials in y, I still have the ability to undo it by just applying the right operator more times. And now we're good. Now we can prove it. So how can we isolate a component? First, what am I trying to do? You know, imagine that we have these two different mixtures, m and m prime. And I tell you that one of the components doesn't match any of the others, either in m or in m prime. So there's one component that stands apart from all the others. What I would love to do is to remove all of the other components. And now I have a method to do that, just by applying differential operators. So let's say that I take, you know, two components just that I can visualize it, G1 and G2, and I apply the differential operator that kills G1. So it's 0, that's good. G2 gets more complicated because we kick out a polynomial in front of it, and that's why it's not even a density function anymore. It has a negative component in front. But now how can I get rid of G2? I can just apply the right differential operator, not once, but twice. And that kills the second component too. So now how does this work? Imagine that you start off with two different mixtures where there's a component in one, in M, that doesn't match any other component, either the other components in M or any of the components in M prime. What can I do is I can just apply a particular sequence of differential operators. You see this first part right here, it kills all of the components in M prime. The second part kills all but one component in M. And what I'll have left over on M prime is 0, because I've killed all the components. And what I have on the left-hand side is not 0, because there's a component where I haven't killed it, and I've just kicked out some gigantic polynomial in front. But that gives identifiability, because the generating functions are different. We've proven it by finding a procedure to use knowledge of the components to isolate one component that doesn't match anything else. And now the magic happens, right? So first, identifiability, I sort of told you that it's really important to only use low degree identifiability. This actually is low degree identifiability. See, the generating function in principle uses infinitely many moments. But if you think about the differential operator as being a polynomial rearrangement, you can see that I haven't applied too high powers of any differential operator. So when I say that the generating functions are different, that I've made one 0 and one non-zero, I don't actually need to pull any information from very, very high terms in the series expansion. They never make it down to the lower order parts where I eventually identify the difference in the generating functions. So I proved actually a lot more for you, which is that one of their f of k degree moments is different. That's not order k, like we managed to do, for k Gaussians types of things, but it's much better in terms of not having to reduce to one dimension. And this part, I'm not going to show you any intuition for, but the basic idea is that if you actually keep track of the errors in these things and want quantitative bounds, it turns out that this type of robust identifiability that I proved for you via generating functions and differential operators turns out to give you dimension-independent polynomial bounds. And at least there's some of the right ingredients there, because I'm only using f of k moments. And I'm keeping the original high dimensional problem around, because reducing to 1D problems isn't always going to work for these kinds of things. And the other thing is that there's this beautiful work of Daniel Kane, which studied the mixture of two Gaussian case. And the way that he did it was by robustly estimating the Hermite moments. It turns out what we can do is we can use his approach, or rather extensions of it to even higher degrees, and robustly estimate Hermite moments of the mixture. And what this will tell us is that we have robust estimates for the Hermite moments of this mixture we started from. And those, in a dimension-independent way, determine the parameters of the mixture. And this is what tells you that, that you're good, that you can get dimension-independent and poly and epsilon types of guarantees. I won't tell you why exactly Hermite moments are so convenient, but maybe you can just believe me on that from a robustness perspective, they're really the right basis for the moments, in the sense that you get very strong quantitative guarantees for how well you can estimate them. So it just plays nicely with a lot of this machinery. So now we've reached the part which I wanted to run out of time before I got to. So I'll take a long 10-minute pause and draw out my words.
Ankur, can I ask you a question?
I guess. Yeah, please.
Thought I would save you. Okay, I thought that, okay, this is super cool that you can go totally via polynomial identifiability or robust identifiability. I thought at some point you still have to rely on some clustering subroutines. Is that true, or am I missing something?
That's absolutely true.
But from the picture you presented so far, it wasn't clear to me why you would need, maybe I just missed this. Why would you need to do clustering at all? It sounds like you have identifiability for arbitrary mixtures via this differential operator thing, which is super slick. So why do you have to go to clustering?
Right, because so the other reason for using I plus sigma for the parameterization is that, if you take for granted what results are known for robustly clustering mixtures of Gaussians, you can in some sense without loss generality assume that you have bounds on mu and sigma. So when you actually prove the quantified versions of these things, you will have some dependence on how well conditioned the overall mixture is. And it's the parts that are really ill conditioned that you can cluster. But you're right that there's nothing like the fractionality of the mixing weights showing up here. It's just when you evaluate when these guarantees are strong enough to give you TV guarantees, you need to handle the clustering case separately.
Wait. Okay, I understood that, except you said the thing about the fractionality of mixing weights, which I know was a contentious point. Sorry, what was that in reference to? That's not showing up.
So that we only inherit through the clustering parts.
Yeah. Okay. I see. Okay, but the point was that the clustering has to happen because in the quantitative error guarantees that you get out of this Hermite's polynomials approach, like some condition number of sigma or something like that is going to show up.
That's right.
Okay, thanks.
In fact, we'll see this, I think, in a second. Yeah, I mean, you'll see a different way to think about this issue.
Okay.
Actually, can I ask a follow-up question to Sam's question? It's so it seems like the bounded fractionality. So part of that is like a lower bound on the minimum mixing weight in terms of like k, right? And so you're saying that somehow to get quantitative bounds on the total variation distance between like two separate pictures, you need all the weights to be lower bounded, like in this approach for proving identifiability.
Right, because if one of the mixing weights was 0, then even if the component did not match, that would not imply anything about their generating functions being different, because it would be 0.
I see, but is it clear that you need some function of k lower bound on W main, or could it actually be much lower?
So I thought here you could use an epsilon, any function of epsilon, like f sub k of epsilon, as a lower bound in the mixing weights. You don't need just a function of k, if I understand correctly.
That's right.
But that's just for the robust identifiability, right? When you go to algorithms, this becomes a different issue.
That's right.
I see.
All right, so let me actually try to say something cogent about SOS. Maybe it'll be the first time I've done it. So anyways, this is all fine and dandy, but we need algorithms. So I guess the main question now that we have some form of robust identifiability is, when we take Daniel Kane's technology and we robustly estimate the Hermite moments, and we know that those suffice, like all you have to do is match those well enough and you're good. Well, how do we actually find parameters that match? You see, when we used to reduce the problem to 1D, it was always a constant number of variables. So there was never an issue. You could brute force look for a solution and it wasn't a big deal. But here, when we're attacking the high dimensional version of the problem, what we really have is we have a system of polynomial equations, because all the unknowns are the parameters in our mixture. They're poly and D parameters. And we want that the Hermite moments defined by those parameters approximately match our robust estimates for the Hermite moments. Now that's kind of a non-starter. You can't solve systems of polynomial equations, but there is something cool that you can do that in many cases is just as good. So there's this beautiful thing called the sum of squares hierarchy introduced by Perlot and Lasserre, which I'll give you the informal idea, is instead of actually solving it, you find something that acts like a solution. So you find something called a pseudo expectation that in some sense acts like a distribution on solutions to the system of polynomial equations, and you find it via solving a large semi-definite program. So the only thing technical that I'll tell you about this is, I'll tell you how to think about what a pseudo expectation is as an object. What it is it's just an operator that maps degree at most q polynomials in D variables to a real value. And the important thing is that it satisfies various low degree consistency constraints. So for example, you want that this operator is linear. So you apply it on the sum of two polynomials, and what it'll spit out is the sum of, it applied to those two polynomials. You want it maps 1 to 1. And one of the main things is that you want that when you put in a square polynomial, it outputs a value that's non-negative. That's the constraint where the action is happening. That's where semi-definite programming comes in, is to enforce this constraint. These are all general constraints, and what you really need are constraints that are specific to your problem in addition to this. But the basic idea is that if you have an object like this, you'd like to think about it as an actual solution. If I had a solution to my system of polynomial equations, the way that I would find a pseudo expectation operator is it would just be the evaluation map. You give me a polynomial and I evaluate that polynomial on the solution to the system of polynomial equations I found. And more generally, if you gave me a distribution on solutions, you would map it to the expected value of the polynomials. Now, what you find is not a distribution on solutions, but it acts like one in the sense that certain types of low degree consistency constraints that you enforce in the semi-definite program are also, enforced by the pseudo-expectation operator. So the important thing is that actually our proof of robust identifiability only used the type of low degree consistency constraint. That's where that f of k showed up, was because there were really polynomial rearrangements happening under the hood. And what I claim is that, you can use that machinery of generating functions and differential operators to prove other related useful identities, like this monstrosity here. So don't try and parse this yourself until, I tell you what to look for. So, we have two mixtures, m and m prime. And the way to think about it is that the left-hand side measures, there's one particular sigma that's different than the others, sigma j prime. It doesn't show up, so the point is that the left-hand side measures how far this one special sigma is from all the other sigmas. That's what it's doing. And the right-hand side measures the discrepancy in the Hermite moments, where h prime are the Hermite moments of the mixture m prime, and h are the Hermite moments of the mixture m. So this is actually the same thing, this is a variant on the theme we've been doing all along. What does this identity tell us? It tells us that, if the Hermite moments are the same across the two mixtures, then sigma j prime has to match one of the other components. Or conversely, if in the contrapositive, if sigma j prime doesn't match any of the other components, one of the Hermite moments must be off. And because this is just a low degree polynomial consistency constraint, it'll actually tell you that the pseudo expectation of the Hermite moments of your candidate solution are off. So to sort of put it another way is that when you take this type of symbolic identity, well, H represents the things I want, the true mixture that I want to estimate. Let me replace those particular Hermite moments with robust estimates of their Hermite moments that I get by using Kaynes' technology. And then I find a pseudo expectation operator where the Hermite moments of my resulting solution I'm looking for, the parameters of a mixture, they are supposed to match the pseudo expectation is supposed to map the Hermite moments to things that are close to the robust estimates. And the important thing is that this identity now implies that our covariances actually must be true to the true covariances. Because if there was any covariance that didn't match, then we could use knowledge of all of the components in the true mixture to derive via differential operators an identity that looks like this, and it's a contradiction. Now, SOS doesn't know which particular sequence of differential operators to apply, because that depends on the parameters of the true mixture. But it checks all of them. So that's good enough. So that's basically all I wanted to say. That was a bit of a sketch at the end, but hopefully I gave you some of the ideas behind why this is actually not so far from an algorithm. So the sort of summary of at least my portion of the talk was I gave you a robust algorithm for parameter learning GMMs, related to the stuff that Pravesh mentioned. So it's exciting to see a lot of, can work parallel and very different techniques for approaching these things. And the main thing that made ours work was a proof of robust identifiability. And to me, the really exciting thing is that, I gave you the proof that we didn't actually have to write some horrible identities, that a lot of the intuition you could garner just from what happens in 1D. So to me, these things look kind of powerful, and I now wonder what else they can be used for. In theoretical machine learning, I have no idea, but if you have ideas, do something with it, do something cool and send me the paper. And also I sort of waved my hands at the fact that this turns into an algorithm in the way that people who do sum of squares always wave their hands. So you should be used to this by now. And I'll stop there and take any questions you might have.
Right, let me maybe get the ball rolling with a high-level question that Pravesh suggested at the end of his talk, and I guess we didn't pick up on. What are other mixtures of distributions that it makes sense to study, more general, quote unquote?
As in like beyond GMMs and stuff, right?
Yeah.
Well, maybe I'll defer to Pravesh on that. I think it sort of depends on which techniques you want to apply. They seem to have different kinds of strengths. So for me personally, one of the things that I was excited to think about after this were some problems about something called orbit retrieval, where I thought that differential operators might be a very useful way to design the first learning algorithms. Forget about robustness. But I think that the techniques that Pravesh described are rather different. So he might have some other ideas about what are the natural next targets.
Yeah, I guess maybe Ankur knows more about this than me, to be honest. But the result of Belkin and Sinha, for example, extended to more general families of mixture models, which also relied on some polynomial relationship between moments of distributions. So I guess maybe I don't know exactly how hard, how easy it is, but maybe it's a very related question to ask, maybe to see if you could do the Belkin-Sinha result, which holds for this polynomial distribution families that they define. Could you also somehow get a robust algorithm for their families, for example?
I see. So there's one more question from the audience.
I think that's a good question, but one of the caveats to keep in mind, actually there are two caveats for that. So the Belkin and Sinha results are not actually effective in terms of K, because they rely on the Hilbert basis theorem to show that a finite number of moments suffice. And also there's some pretty neat examples in 1D, but in higher D, I'm not entirely, it's a bit trickier to find examples which are polynomial mixture families and their notation. But maybe exponential families could be an interesting one, for example.
There's one more question from the audience. Maybe you can feel free to unmute yourself. If not, I'll just read it out. All right, I guess I'll just read it out. So as Amir understands it, this way of thinking seems to allow for a large number of outliers. In which case, does this extend to the list decodable setting? Either one of the speakers can field this one.
Yeah, so I guess I don't think it extends to list decodable setting. In fact, I feel like the list decodable setting is actually really more challenging in this setting. So just to be clear, I guess the question is about the following model. So let me be just state it precisely, right? So imagine that there is some parameter alpha, which you think of as 1 over k. And now, your input is a sample where, let's say, 1 over k fraction of the samples come from some Gaussian distribution. So with an arbitrary mean and arbitrary covariance. And the rest of them are, imagine adversarial outliers. And so in the list decodable setting, you're thinking about, this alpha being 1 over k. So in some sense, think of k equals 10. So 10% of the samples are inliers and 90% are outliers. It certainly generalizes the clustering setting because, in some sense, you can always think of one of the components as inliers and everything else as outliers. But it's certainly more general because you have no guarantees on the rest of the, data. And the goal in this setting is to come up with a list of parameters such that, one of them is close, let's say in total variation distance to the Gaussian, that define the original set of inliers. And so it is related to this problem, but at least my sense currently is that it definitely requires new ideas to solve.
Great, thanks. Ankur seems to concur. All right, so I guess this is a much longer talk than usual with a lot of interesting insights. So thanks again to our speakers, Pravesh and Ankur. Great, so this is, I guess, the last talk, TCS Plus talk of the semester. So hopefully see you all in another semester when video talks will become a luxury rather than a necessity. With that, wishing everybody a fruitful and relaxing summer. Bye, everyone.